In this talk, I will introduce our latest work on designing a new type of display called low-latency beaming display, which project images sticking to the field of view during the fast head movement. This is a joint work between the University of Tokyo and Tokyo Tech. First, I'd like to introduce the motivation for our work. This work is a type of optical see-through head-mounted display. In recent years, optical see-through HMDs have been introduced to the market. However, these commercial OST HMDs have faced the challenge of creating a small form factor. While packing all of these sophisticated components into a module, such as optics, sensors, computers, and light engines with more stringent power constraints. Beaming displays attempt to solve the trade-off between form factors and specifications in conventional OST HMDs by isolating the projection modules and computing resources from the headset to the external environment. The user wears a lightweight, passive wearable headset. Then the external steering projector tracks the user's head movement and presents images to the eye position. However, beaming displays face a significant challenge: motion to photon M2P, latency, the latency between the user's head movement and the image displayed. The beaming display imposes stricter M2P latency constraints than conventional OST HMDs because it continuously projects small images from a distance onto a few centimeter passive screen. On the other hand, this prototype relies on AR marker-based tracking, which results in a 7.7 millisecond motion to photon latency. In previous research, Lincoln et al. Developed low-latency benchtop OST systems with low M2P latency using rotary encoders and FPGA, achieving 80 microseconds latency. However, this system can only track head orientation and should integrate all components into the headset, resulting in a large form factor. Also, low-latency outside-in head tracking system is proposed by Blate et al., which achieves 28 milliseconds latency. In their system, emitters on the headset emit light as a position signals, and two-dimensional lateral effects photodiodes detect the difference between the center position and incident light. Although it lacks image display capability, we are inspired by this study. Because this configuration is particularly compatible with the beaming displays, so that emitters are inside the headset and the detector is placed on the external environment. Based on the low-latency head tracking system described before, we propose a low-latency beaming display system. In our system, we attach an emitter that informs the current head position to the wearable headset, and we add a 2D lateral effect position sensor inside the steering projector that is coaxially aligned with a projector. Let me describe how this system actually works. When the system is aligned, the emitter on the headset emits light that reaches the center of the 2D position sensor in the projection module. At this time, the projected image reaches the screen on the headset via the steering mirror, allowing the eye to see the image. Next, consider moving the position of the headset. In this case, if the mirror angle remains the same, the image will not reach the eyes. The light from the emitter incoming to the position sensor also moves from the center. The position sensor sends this misalignment as an analog signal to the mirror controller, which controls the steering mirror to return the misalignment to the center. As a result, the projected image is again localized to the same screen position. This feedback is controlled by a fast 10 kHz closed loop, without the need for intervening digitization processes such as image processing. As a result, the projected image follows the moving headset as seen in the video. This video shows the results captured from the viewpoint camera while moving the headset. Please note that our system currently only supports horizontal and vertical movement, so any depth movement will result in defocus blur. The video confirms that our prototype follows the movement of the headset while presenting the image in front of the eye. The projected images have reduced spatial resolution due to jitter in the mirror control, which I will describe later. Using the prototype, we evaluated the latency of our system. We mounted a reference light and a projection light on a linear slider in opposite directions, and we moved the slider left and right 20 times. Then we recorded their trajectories, and then estimated the latency using the correlation-based latency estimation. As a result, the latency of our system was 133 micromilliseconds, which is 1/58 of the original system. We also estimate the accuracy of our system. We removed the horizontal offset from the trajectories and calculated the errors. The error was less than 2.58 millimeters, which is 14% of the horizontal image span. From the frequency analysis of the error, there is the jitter above 27 Hz. By removing the jitter, the error was less than 1.63 millimeters. In this paper, we discussed the remaining challenges of our system, including a retroreflective design to make the headset completely battery-free, and a 6 degrees of freedom tracking design using triangulation, a control law for stable tracking, and a fast image warping function. Especially for 6 degrees of freedom tracking, please check our poster on a dual beaming display that synchronously controls and projects multiple projection modules. We presented our low-latency beaming display prototype with analog closed-loop control using a 2D position sensor operating at 133 microseconds motion to photon latency.